This video is on nuclear stability. So, a nucleus, here's an example of a helium nucleus, is made up of protons with a positive charge and a neutron with negative charge. So helium nucleus has 2 protons and 2 neutrons. Now, one of the forces at play is the electromagnetic force. So we learned last semester that if you have charges of the same type, they push each other away. So there's a repulsive, which means push away, electromagnetic force. Sometimes that's called a Coulomb force. And again, last semester we learned about Coulomb's law, where the force equals K, big Q little q on d squared. So we know that the force depends on how far apart, the distance between them. So for example, if you have 2 protons this distance away, the force may be small, and if we then had them this far away, it'd be much smaller. Okay, because, well, they're much further away, so there's a smaller force. So therefore, because of this electromagnetic force, all nuclei with more than one proton at least are inherently unstable. So how can a nucleus possibly stay together? There's another force at play. So we've got the electromagnetic force, that's repulsive, so repel, but we have something called the strong nuclear force, and that's attractive. So what's the strong nuclear force? That's just an attractive force between nucleons. Now, protons and neutrons are in a family of things called nucleons. Okay, so there's an attractive force between 2 protons as well that we've never discussed before, because a proton's a nucleon, this proton's a nucleon, so they actually, in some conditions, do attract each other due to this strong nuclear force. These two, the proton and the neutron, they attract each other due to the strong nuclear force. These attract each other, these attract each other, and so do these. Okay, across here they attract one another, across there they attract one another as well. So there's lots and lots of attractive forces due to the strong nuclear force between neighbouring nucleons. Now, they have to be neighbouring because this force acts over a very small distance, whereas electromagnetic force can actually act at reasonable distances apart. Okay, so maybe we might actually have a situation where these two and these two are actually too far apart to have a strong nuclear attractive force. Okay, whereas, you know, they can be quite far apart and still have a repulsive electromagnetic force. Now, what causes these 2 forces? We don't know, so we don't go into it at all. That's under investigation with physicists right now. That's the frontier of physics, studying what causes these mysterious forces that we know exist. So, what is it? In a summary, a nucleus is inherently unstable due to a repulsive electromagnetic force, but glued together with the strong nuclear force between nucleons, which are protons and neutrons. So let's have a look at this graph now. So when you read a graph like this, it looks really complicated. There's lots of labels everywhere. Always, first thing to do is look at the axis, the y-axis, the x-axis, because that's the most important feature if you are to have any understanding of what these lines represent. So on the y-axis, that's the force between nucleons. Now, it's not so important what it's measured in, 10 to the negative 4 newtons. We might even just get rid of that for now, just to unclutter it, so I can show you how I think about graphs when I first see them. Okay, I don't even need these numbers. Okay, and I might get rid of all this clutter just for now. There we go, and that'll probably do. I'll get rid of this line too, it's not so important for what we want to talk about. Okay, so the y is basically the force between the nucleons, and the x-axis is the nucleon separation. This one's measured in femtometers. 1 femtometer is 1 by 10 to the negative 15 meters. So it's just converting from femtometers to meters basically. Again, to understand the graph, that's not important. Force between the nucleons, how far they're separated. Okay, let's look at the Coulomb repulsion between two protons, this dashed blue line. This is a graph that we've seen before. If two protons are separated by a big distance, they put a very small force. But if they're separated by a small distance, you get quite a big force. Did I say that right before? Hang on. Big distance, you get a very small force. Small distance, you get a big force. If we make the distance between nucleons even smaller distance, you get even greater force. So that explains the trends on this blue dotted line here, the Coulomb repulsion. Now, the strong nuclear force between two nucleons is much more mysterious, and I don't have an explanation that explains this trend line, but we can definitely describe what's happening. As I said before, if you're beyond 3 femtometers apart, you don't actually have any measurable attractive force. Okay, so notice here at this point, this is on the x-axis, meaning the force is 0. Okay, so beyond here, let's say at 4 femtometers apart, it's still 0. There's no strong nuclear force. Okay, but there is still a measurable electromagnetic force at 4 femtometers apart. I might even just include that. Let's say it's 4 femtometers apart there. Okay, so the strong nuclear force is 0, but the electromagnetic repulsive force is measurable. Once we get a bit closer, 3 femtometers apart, we start to experience a force between them, and it's just gradually increases, and so it's a bit of an attractive force when the nucleons are 2 femtometers apart, and then suddenly dramatically the attractive force really increases. So there's its peak at probably just over 1 femtometer apart. You get amazing attractive force, and look how much bigger this force is compared with the electromagnetic force. Okay, so you've got all this strong nuclear attractive force, a little bit of repulsive force compared to that, and so then of course you're going to have a stable nucleus. The attractive force is far stronger than a repulsive force. Okay, and of course you can get to here, where the repulsive force is about the same as the attractive force, and there'll be another spot over in here somewhere as well. So there's basically a sweet spot of distance between two nucleons where the strong nuclear force is larger than the repulsive electromagnetic force. Okay, as we said, electromagnetic force can act over much larger distances than the strong nuclear force. So when you get big nuclei, like I think I've said before, lead is once you've got more protons than lead, which is 82, you're radioactive, because 83 protons or more is too many for the nucleus to be stable. So if you think about it, it makes sense, because just say we had this nucleus, something like that. Okay, so all the neighbours attract each other, okay, but probably not really more than neighbours. But look at this, these two, they're way across from each other. They still would exert a repulsive force. These ones would, Okay, so that repulsive force is acting over a great distance. So while you might have more, I suppose, bonds between the neighbours, they're only ever acting at the neighbouring level, at close distances. So that's why I was saying once you get 83 protons, there's too many networks of repulsion across that nucleus that it doesn't matter how many neutrons you've got to sort of keep them separated, they interact too strongly and the nucleus breaks down, it's unstable. Okay, so yeah, in summary, this graph, we've got repulsive force up here, attractive force down here, nuclear separation, you can see the two types of forces, and there's a sweet spot in here where the strong nuclear force is greater than the electromagnetic repulsive force, meaning that region is, of nuclear separation is where you want it to be if you want a stable nucleus.